This is Advanced Functions section 3.3, Characteristics of Polynomial Functions in Factor Form. Let's start with the parent function of the graph x to the power of 3. It's a cubic function. The shape of the graph at the origin is called a saddle. So that shape you see that curves up like that is called a saddle or a bend. And it's kind of unique to cubics or cubic roots, which we'll talk about in a minute. In this case, the function is continuously increasing, but the rate of increase slows down. So it's, if you imagine tangent lines all along here, they're pretty steep, then they start to flatten out for sure. The rate of change is decreasing here, and then it increases again. It gets faster and faster. But the function itself is always increasing from left to right. It's always getting a little bit higher, a little bit higher.
So here's our cubic parent function with no transformations. If you look here, you can see that's just x times x times x. If I change any of these factors here, let me put an x minus 1 in the first bracket. Let's make it a bit bigger so you can see it. X minus 2. So now we have an x-intercept or a 0 or a root at 2. This bracket factor gives me a 0 at 2. This is a 0. These give me the zeros here. Now notice these two x's together, they're an x squared, right? That gives me that squared shape, that parabolic shape right there. Let's change this around a little bit more and get some other numbers. About a 1 there. So looking at these factors, x minus 2 gives me a root or an x-intercept at positive 2. X plus 3 gives me a root or an x-intercept at x minus 3, at negative 3. And this final factor gives me an x-intercept at 1. So I've got 3 different ones. So what happens if some of these are the same? Or let's make them all the same. Let's make them all x minus, well, let's do x minus 3. Make them all x minus 3. When we make them all x minus 3, if I zoom in here a bit, it's back to looking like that cubic we saw with this bend shape or the saddle shape here. So no matter how far I zoom in, my function only crosses the x-axis at 3. It slows down, its rate of increase slows down, it gets almost flat there, it crosses at 3, and then it speeds up again. Center that back up again. So when all 3 factors are the same, we have a cubic factor, or x minus 3 to the power of 3, we're going to get that bend shape there. Whereas if we had something like this, these factors are called linear factors because there's only one of each of them. When you have a linear factor, that means its exponent is a 1 on each of the little brackets. They look like a linear segment right here around the x-axis. So we have a linear piece here, a linear piece here, and a linear piece here when our factors are linear. Let's see if we have a squared factor. So if we have 2 of them the same, we have x plus 1 the same, so that would be the same as writing x plus 1 squared. We have a parabolic shape there, like a quadratic shape. The x minus 3, there's only one of them, so it's a straight through. It goes straight through the x-axis there. So if the factor is squared, then the graph has a parabolic shape. If the factor is linear, it has a straight through or a linear shape. And if the factor is cubed, then we have, let's get that up there, then we have a cubic shape at that factor. So another word you'll see in your homework is the word order. So this would be x plus 1, that it would have an order of 3 because there would be 3 of them. Now the x plus 1 would just have an order of 2 because there's 2 of them. So order or the degree of the factor, you'll see any of those. Let's put in a 4th factor here. So now we've got a quartic. Let me zoom out. See that quartic shape? It's that W shape. So there's a quartic. We've got a parabolic root here because we have x plus 1 twice. And then we have a straight through at x equals 2 and a straight through at x equals 4. So let's make some of these the same. What happens if we make two of the factors the same? So I'm going to just make this one, make both of these a 4 here. So there's our W shape. But as you can see, we have parabolic, we have a bounce here. That's another word for this here. When your intercept comes down and goes back up, we have a bounce. So we have a bounce root at -1 and we have a bounce root at 4. Let's make 3 of them the same. So we make 3 of them the same. It's still a quartic, it's still a degree 4, but we have a bend here, or we have a saddle root here when x is -1, and we have a linear or a straight through when x is 4. So the last thing we want to see is what happens when all 4 roots are the same here for a quartic. We have, when all 4 of them are the same, we have an order of 4, or a factor of the 4th degree. This, if I zoom in, it looks like a parabola, but a quartic really flattens out along the bottom. So, sorry, it looks like a quadratic is what I meant to say, but it really flattens out along the bottom. The quartic, it has a slower pace, changes here, slows down. Very slowly. The rate, if I was drawing tangent lines, they would be almost horizontal along here, and then they speed right up again.
Example 1, we're going to sketch a possible graph of this function in factored form. That's our whole topic, is everything is in factored form. So it says possible here. Why does it say possible? We're going to learn transformations and more specifics later. Today, we just know about end behavior, which we've already learned, based on the leading coefficient and the degree. And we can use the factored form to illustrate the zeros. So we're going to use some of the characteristics that we know, and we're going to draw a possible graph from that. So the degree is 3. It's a cubic function. I know it's a 3 because if I expanded all of this out into standard form, if this were a power of 2, I wrote another bracket of x minus 5, and just distributing the x's, I would have a single x here multiplied by a single x here multiplied by another single x, I would get x to the power of 3. So it's a cubic function. It has a 0 at -2. That's this one. And that's going to be a straight through one, a linear one. It's just going to cut through at -2. This factor is going to give us a bounce at 5. So we're going to put on the x-axis. We're going to draw the x-axis, and we're going to put scale just on the x-axis right now. I'm not sure about my y-axis, but I know I want to be able to get this -2 and this 5 on here. So I'm going to count by ones, and I'm going to label my x-axis. All right, so we've put that information on. Notice, remember we have a bounce at x equals 5. I don't know if this is going to bounce up like this, if the parabolic shape is going to be like it's opening up, or if it's going to be opening down. So we're going to get some more information. So far all we have are those 2 zeros. The next thing is the y-intercept. It's an easy one to find. You just sub in a 0 in for x's, you get a y-intercept of 50. So that now tells me I'm going to use a y-axis scale. I'm going to count by intervals of 10. Although I counted by tens, I only labeled every second one just because it's crowded and it's messy writing on this with this pen. So I'm counting by tens, but I'm only labeling 20s. So I've got now this piece on, the y-intercept. So that helps me to see how this graph is going to look. What else can we tell? Well, the leading coefficient is positive. The leading coefficient, we talked about that. The leading coefficient would be a positive 1. It would be positive 1x cubed would be our leading term. So the leading coefficient is a positive 1. That means the graph is going to start down here, and it's going to be cubic. So we know what cubics look like now. It's going to kind of turn around and come down and bounce up here and land in the fourth quadrant. So I now know that my bounce is opening up as opposed to opening down because my leading coefficient is positive. So it has to be increasing. Once I'm done all this turning around, it has to be increasing. As x approaches infinity, my y has to be approaching positive infinity as well. So when I'm going to draw my graph, and I'm going to come around like this, I'm not going to turn. The tendency is just to turn right there at the y-intercept. It probably wouldn't turn there. It would probably go a little further and turn up here. I don't know exactly where. I don't know that yet. I might have to wait for calculus to know that turning point exactly. But that's why this is a possible graph. This is just a possible graph, so I'm just going to fill in what I can. There we have a possible sketch of f at x. We're going to do another example like that. Sketch a possible graph of, this time is a little different. It's very similar to the previous example, but it is just a little bit more different. We're going to start with listing some characteristics of the function. So here's the graph. What I would normally do in class, if I were teaching this in class, I would ask you guys to tell me what are some characteristics you can tell by looking at this function. What are some things you can tell me, any characteristics at all? So try to think of one, or try to think of a couple. What can you tell me about this graph here? So hopefully what one of you is thinking is that it's quartic. Its degree is 4. This x would be squared, this x would be squared. So I know it's going to have a W shape, quartic, or an M shape if it's opening down. It could be also flattened in the middle like some quartics are. What else? There are bounce zeros. Both of these are bounce zeros because the order of these factors is 2. So this is like a little mini parabola right here, and this is a little mini parabola right here. So let's put those on first. Again, I'm going to start with labeling my x-axis. I'm going to count by ones on my x-axis, and I'm going to get those intercepts put on with a dot. So I've put those on, the scale and the 2 bounces. Other thing we know is that f at 0 is 100 by subbing in 0. So there's my y-intercept. Now I can use my scale. I can figure out my scale for the y-axis. I can't count by 10s this time. I'm going to have to count by 20s, I think. So press pause, put your y-axis scale on, and put your y-intercept on as well. All right, so I've put that on. Now the leading coefficient is positive. I know that, again, the leading coefficient for this one is also a +1, so this is going to open up. Now that means I know that my bounce intercepts are both going to bounce up. This is going to bounce up, and this one's going to bounce up, and that's why I'm going to get that W shape. So I'm going to draw a W shape coming down like this, not necessarily turning here, maybe turning up a little higher, coming back down, and a W shape there. So press pause. Sorry, parabolic shape. Press pause and put that in. All right, I've got a W shape going on there. The last thing we can do is you can sub in test values in between the zeros and on the outside of the zeros just to get an idea of the location. So if you're not quite sure if you've got this shape right, you can sub in. So I picked f at -3. So f at -3 is on the outside of this 0. I just want to make sure I'm in the right space. So f at -3 I got to be a 64. So I didn't put that in the right. I should have curved this up a lot higher, but that's okay. What's important is that this is a positive 64. If I would have got a negative 64, then I'm making a mistake because I'm not in the right quadrant. So these test points help us to make sure we're in the right quadrant, and I could erase that and stretch it up a little bit more. But the important part is that we're getting the positive value there. If you'd like to look at another example like this, our textbook has one on page 140. Another example like both of these, example 1 and example 2. So you can try some more there or look at some more insight on how to graph. From grade 11, remember that families of functions share certain properties. If a few functions share the same zeros and they have the same degree, they're in the same family. Determine the equation of the function shown. Start by listing some characteristics. Okay, you've got some ideas in mind here, what some characteristics are that we can tell. From the shape of the graph, we can tell that it's cubic. So that's important. The equation is going to have this form then. It's going to have an a value, maybe. The one so far we've only had a values of 1, but this maybe not be a 1. And we're going to have 3 roots, 3 factors. The zeros, I can tell by looking at the graph, there's a 0 at -3, there's one at 1, and there's one at 2. And they're all linear, they're all straight through. So I'm not going to have any bounces or any degrees of 2. So that takes me from this factored form into putting some values in there. Now we have to find the a value. So just like we've always done since grade 10, to find the a value, we're going to sub in. So let's go to our equation. We're going to use this point 0, 3 right here, and we're going to sub, this is our x, this is our y. We'll put it into the equation that we have so far, right here, and we get 3 equals a 0 plus 3, 0 minus 1, and 0 minus 2. So we tidy that up. That's a 3, that's a -1, and that's a -2. Putting all that information together, 3 equals, so I'm going to multiply these 3 together. That's going to give me a +6. Divide both sides by 6, and I get 1/2 equals a. And we keep it as a fraction, you don't change it to a decimal and write 0.5. So our equation is y equals 1/2 x plus 3, x minus 1, and x minus 2. And that's the equation of this function. And if you want to see some more examples like that, your textbook has a few on page 141 and page 144 if you want to practice some more of those with examples. So the examples help you because they show you steps like I did here. It's not just a homework question that you have to figure it on your own. The textbook, you can read some more examples there. Example 4, sketch the graph of this function. Okay, this one is in standard form. It's not factored, and we have, right now our whole lesson is on factored form, so we have to get this into factored form. So we're going to have to factor. We've never factored anything with a power of 5 before, but hopefully you notice that there's a greatest common factor of -2x cubed. If I factor out the -2x cubed, then I have something a lot more manageable. I have a nice little trinomial here, back to grade 10. You can use sum and product or decomposition, whatever method you use, crisscross. It's an easy trinomial. It factors nicely like that. And one final thing we can do, if you notice this x minus 3 is written twice, we can just write it more compactly like this. So now we're back to a question that, like the examples that we just did. It's in factored form. So it's in factored form. What can you tell me about the equation? So take a look at the equation, come up with some ideas, and I'll give you a second to think about that, and we'll see if we have similar ideas. The easiest ones to come up with are the ones from the standard form. The degree is 5 and the leading coefficient is a negative. So remember that a degree of 5, when you have an odd degree, you're going to have one end up and one end down. You have opposite end behavior. So we have a degree of 5, and then we also have a negative leading coefficient. Negative leading coefficient. What else have we got? Well, when I look at the, let's start with the bracketed factored part there, x minus 3 squared, that tells me I'm going to have a bounce. I'm going to have a bounce intercept. That's coming from this bracket right here. My bounce intercept when x is 3. My first factor, it's cubed, so it's going to be a saddle or a bend, saddle or bend intercept at x equals 0. So now that we have those, we can go ahead and put our scale on our x-axis and put those intercepts on. Now this one has already we know the y-intercept is going to be 0. We already have 0, 0. And if I wasn't sure of that, just sub in 0. We've got 0, we've got x's everywhere here. So this is going to be, so our y-intercept is going to be a 0, 0. So that doesn't really help us with the scale for our y-axis. But we can come up with a few kind of test points in between the zeros. We can come up with a point in between maybe these zeros here, or on the right of 3, or on the left of 0. Just to get an idea of a scale and to figure out what to do there. So I've gone ahead and found 2 points, f at 1 and f at -1. My y-axis, if I want to fit that f at -1 on there by 32, I just want to make sure to scale it so that it fits. All right, I think we've got enough to go on now with these points. For the degree is 5, but what's important here is I've got a bounce, or a bounce at 3 and a bend at 0. So because of this point here, I know that I'm going to have to bend in this direction here, come down, turn around somewhere, and then bounce up again. I can't be bouncing up here because I can't cut through again. I have no other x-intercepts. You should not be crossing your x-axis anywhere except here and here. And we're actually crossing here, we're bouncing here. So we have a degree of 5 and a negative leading coefficient. That means our function is going to start up here, it's going to do some interesting stuff, and then it's going to end down here. It's got to be decreasing its end behavior as x approaches infinity. It's got to be coming down to -infinity. So we'll just come up with a possible graph here and draw it in. All right, so I'm no artist, but we've got my bend right here, and then I'm turning around somewhere, I don't know where. But then I definitely have a bounce coming down here, and this end behavior as x approaches infinity is approaching -infinity. Page 143 has another example like this. If you want to try another one like this, please go there and take a look. Long division. Okay, going back to elementary school, this is kind of an aside that we need because sometimes we're not given our equations in factored form and we have to factor them. So let's do some review here. Different students, different teachers teach long division in different ways. So I'm going to just review this method here, which I hope is familiar to most of you already. What we're going to do with long division is I'm going to take this 4 and I'm first going to divide it into 8. Forget about the 72. I'm going to divide 4 into 8. That's my first step. So 4 goes into 8 twice. I'm going to put the 2 on top. The next step with long division is I take that 2, I multiply it back down to the 4, and it happens to be exactly 8. It doesn't always work out that way, but I'm going to put an 8 down here. That's my first step. Okay. Then I draw a line and subtract. 8 subtract 8 is 0. I need to bring down the 7. You remember that step? So I'm going to bring down the 7 here. Now I'm going to change colors so that maybe it helps you to see the steps a little better. I don't know why that's erasing. So I'm going to bring down a 7. Okay, now I start it all over again. I brought down the 7. So I'm going to do 4 divided by 7. I'm going to take the 4 and I'm going to put it into the 7 this time. So I'm doing 4 divided by 7 now, dividing here. 4 goes into 7. How many times? Once. It only goes once, can't go in twice. Now I have to take that 1, multiply it back into the 4. 1 times 4 is 4. I put it under here. Subtract. Subtract. 7 minus 4 is 3. And then I bring down the 2. 32. Okay, another color. Do the whole process, the whole kind of algorithmic process again. This time I'm taking my 4 and I'm dividing it into the 32. 4 goes into 32 evenly, luckily for us, 8 times. Then I multiply that 8 back into the 4. 8 times 4 is 32. When we subtract these, we get what's called a remainder of 0. And we're only going to have remainders of 0 for now. So that's how we did long division back when we did division, those steps there. Another way of writing it is 872 divided by 4 is 218. This number is called the dividend This is the divisor, and this is the quotient. So why did I do that? Okay, we've got x plus 2 is a factor of this polynomial, but it's not in factored form, and we only know how to work with factored form right now, so I'm going to have to get this into factored form. We're going to use polynomial division to find the other factors or the zeros, because I don't have a greatest common factor here like I did in the previous example that I could just take out. I have one factor, so I'm going to turn that into division, just like this. So this is a more complicated than what we did with just the numbers, so you might need to watch this more than once. I just take this x first, and I'm going to divide it into just this first x. So this is the equivalent of what I did in red the first time. I did 4 into 8. That was my first step right there. So x into x cubed, let me just put that off on the side here. I'm doing x cubed divided by x. That is going to be x squared. So I'm going to put the x squared up here. So I'm still looking over to what I did before in red. My next step, once I got that 2, was to multiply it back down. So I'm going to multiply it back into both. No, this is where this binomial becomes important. X squared into both of those. So x squared times x is x cubed, and then x squared times 2 is positive 2x squared. So we're going to subtract the whole thing, not just the first term. I need to subtract both of them. So first I'm going to do x cubed minus x cubed, that'll be a 0, but then I'm going to do negative x squared subtract 2x. So negative x squared, so these two are gone, they make a 0. The x cubes are gone. Negative x cubed subtract 2x is negative 3x squared. Okay, that's the first step. Now, moving along, I've got to bring down the 16, negative 16. So that's a negative 16x, that comes down. So now I'm on to my second step here. I'm going to take my first term again, I'm underlining it in green. I'm going to divide it into my first term. It's always first term into the first term. So I'm going to take this x and I'm going to divide it into negative 3x squared. I'm going to put it over on the side. I'm taking negative 3x squared and I'm dividing it by x. That will give me negative 3x. So negative 3x goes on the top. It's part of the quotient now. Negative 3x. Now we're repeating the whole step, the whole process again. I'm going to take this negative 3x and I'm going to multiply it into both parts of the binomial. Negative 3x times x is negative 3x squared. It matches, it should, because we worked it out that way. Negative 3x times 2 is negative 6x. And we subtract. When we subtract, these are gone. I'm left with negative 16x minus negative 6x. Be careful with those signs. That's actually negative 16x plus 6x. So that's negative 10x. And that's the end of the second step. So I've got to keep going. I bring down the negative 20, and I start it all over again. I go back up to my binomial here, x plus 2. I take the first term, which is the x, I divide it into this first term here. That means on the side, I'll show you I'm doing negative 10x divided by x. That is negative 10. This goes up into my quotient, negative 10. So the pattern repeats. Now I take my negative 10, I multiply it into both parts of this binomial. Negative 10 times x is negative 10x. It matches, which it's supposed to. And negative 10 times 2 is negative 20. And it does match. It won't always, but it does for now. Subtract. Negative 10, subtract negative 10 is really negative 10 plus 10. So they're gone, and negative 20 plus 20, they're gone as well. So we have a remainder of 0. We'll talk about remainders in another lesson. So we have a remainder of 0. Well, what that means is, let me start with the original polynomial. X cubed minus x squared minus 16x minus 20 is equal to the factor I was given, which is x plus 2, and then if I multiplied that by x squared, I'm taking quotient, minus 3x minus 10. That is factored now. We've divided it. Now, can we factor any further? Yes, we can factor this piece here. The trinomial can be factored some more. So that's x plus 2. And then this is a sum and product, so I'm looking for two numbers that multiply to give me a negative 10, and they have a sum of negative 3. And then I can put those numbers right into the brackets. That's going to be an x minus 5 and an x plus 2. So the final answer here, if I simplify it a little bit more, I've got x plus 2, I've got two of those, and then I've got x minus 5. So now I'm ready to graph. So that's a complicated topic for sure, because we haven't done long division for so long. Normally I would stop there, but I'm going to put a bonus practice question up here. I want you to try it. I want you to press pause right now and do this question, and when you come back I will have the whole solution here. I'm not going to go through the step by step. I want you to do the step by step, but I will show you the work. So press pause please and give it a try. So there you have it, the final solution. Please make sure if you are in my class and you're using the handout that you look at there's some important stuff at the bottom of your handout for how to do your homework. So there are other videos as well you can watch on long division. The main part of today's lesson is factoring. So the main part of this lesson is not factoring. The main part is knowing how to graph this right here, right? Knowing what kind of intercepts to draw and leading behavior and all that information. But when you were given questions in standard form and it hasn't been factored, you do have to know how to factor them. So that's what this kind of extra bit at the end was for, but really make sure you understand how to graph these as well. That's the end.